Good afternoon, everyone. I don't know if you need me to do some problems in binomial. If you'd like me to do a problem there, could you let me know in preparation for the quiz at 6 o'clock? So I said everything. The quiz would be up until page 14, I guess. So if you don't have any questions, I'm going to go ahead and work with the sampling distribution of the statistic. I'm going to continue what I discussed there. Unfortunately, yesterday I didn't have my studio microphone on, so the sound was terrible, but I hope you were able to catch the review in among my other videos that I posted in Moodle. I provided a link in the description of yesterday's video as well. All right, so what we were doing, if you don't have any questions about binomial, is discussing the sampling distribution of a statistic. And we talked about three statistics for which we are going to talk about their distribution. So we spent, up until this point, I introduced the idea of distributions, right? So we talked about continuous distributions, discrete distributions, and in particular, one discrete distribution that I promised we would focus on was the binomial distribution. So we talked about the binomial, and then I wanted to go into sampling distributions. So these are distributions for statistics. So as I explained, there's three kinds of statistics that we're going to derive distributions for and use them. One is the count variable x, the number of successes in n independent trials. Another statistic is p hat, which is the proportion of successes in n independent trials. And then after that, we're going to talk about the sample mean as a statistic for which we're going to derive the distribution. So the idea is, although from one sample you would calculate any one of these as a statistic, that statistic comes from a distribution. And we're talking about what that distribution looks like, okay? That's the sampling distribution of the statistic. So the first thing is I spent time talking about, and I have it all summarized as I promised in the last pages where the formula sheet is. You can use this sheet. You can keep it at your side, front and center when you study. Basically, this is what you need for the final exam, okay? And it's all summarized here. You need to understand these formulas, not just use these formulas or attempt to use them. So the first one was we talked about the distribution for x, the count variable, and I mentioned that you could calculate the mean and standard deviation, and then I went into derive these formula. First by rationalizing how that arises, and then proving to you how I could derive those using the rules of means and variances. I also introduced this, and I explain where this formula comes from, so go back at the videos if you still don't understand this formula. And then yesterday I spent time talking about the distribution of x. Although it's binomial, for sure, because that's how it's defined, as a discrete distribution, it's also approximately normally distributed in certain instances. So it's also a continuous distribution. It also comes from a distribution that is continuous and particularly normal. So that means it's regular. It has a regular pattern, and we can make predictions, reliable predictions, in this case an approximation, as long as n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10. The distribution is approximately normal, where the population size is we say large. And that's the terminology I'm going to use. I'm going to be more specific about conditions for large in a bit, but for now it's just if you're told that a population is large, and that really means large relative to the sample, okay? Or if it says large, you know that you can do this. You can apply these formula. So going back to page here. So this is where we left off. And I was talking about the proportion as opposed to the count. And I mentioned that if you want the distribution of the proportion, wouldn't you expect that its distribution is similar to the count, because the count is distributed normal with a mean of approximately normal, with a mean of, well, I'll put it like the symbols, right? With its mean and its standard deviation. And then I gave you formula for calculating those. That's a U. And the formulas were, let me take that off and put the formulas in there instead. NP and NP 1 minus P square root. All right. And then I suggested, well, if P hat comes from X divided by N, shouldn't its parameters come from the original parameters divided by N? By the rules of mean and variances, yes, that's true. By the rules of means and variances and the fact that random trials are independent, all I have to do is divide these by N. So that's what I do. I divide this by N to get the new mean, and I divide this by N to get the new standard deviation. Okay, so let's look at this. So if you divide this by N, and P divided by N is just P, and P 1 minus P over N, times N square root, when you do the math, and I've done it down here, so if I divide this by N, that's easy. Those cancel, leaving P. But what if I divide this by N? Well, to be able to, I mean, you could leave it this way. You could just leave it like this. Or you can simplify it, and if you simplify it algebraically, you put the N inside of here, so you have to square it to put it under the square root sign. And then you can cancel the N's, like one N here with this N here. I can't seem to hit it. So one N and one of those, okay? And then that's why you get that form of the new standard deviation. So it's going to be P times 1 minus P, so probability of success times the probability of failure divided by N with a square root around it. All right, so what do I use this for? So what we did the same thing. We use this for this problem here. Let's say we define a variable as binomial. So we're going to repeatedly look for something in a sample of 100. That's the idea. So we're going to repeat looking for a success 100 times, where the probability of a success is 1/3. So why would we do this? That's another question, and I'll get to that. Why we would do this is another question. But essentially I can. With the theory, given the theory, then I could predict what the probability of having more than 23 successes, if I did that, what that would be. So we did that yesterday. But what if I'm not interested in the number of successes, I'm interested in the proportion of successes. So out of 100, that means I'm looking for 23%. So all I do is I recast the problem as a percentage rather than a count, and I solve this. So we begin solving this problem for the proportion. These are the steps that I've laid out here. Step 1, as above. It means you need to check, and we did it before, that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. So that's the step 1, and it works, okay, in this problem. The next step is derive the mean and standard deviation for the proportion. Now we're going to use these new formulas. The mean of the sample proportion is the actual proportion. Now you can just replicate that, you could just copy that and not understand it, but it would be much better if you understand what that's saying. It's saying if you repeatedly sample, if you have a number of different samples of the same size from the same population, then overall, on average, you expect to see that the proportion you calculate, the proportion of successes, on average, is the actual proportion. Okay, that's what we expect. Otherwise, why would we be doing what we're doing? Why would we be sampling if we didn't anticipate that we could accurately capture the true proportion or the true parameter, the actual parameter? So that's what that's saying there. It's very philosophical, but anyway, mathematically I can prove it as well. So this is what I expect to see. And then the standard deviation you can calculate like that. Now what do I do with that? Using those parameters, now I can standardize to solve this question. So in this case, if the conditions apply, I can answer this question using the tools of Unit 2 NOR, and I don't have to use the binomial formula from Unit 5. All right, so this is a new approach using the normal distribution. So I standardize, that becomes a z because I'm just standardizing it. This is a new value, and so I need to solve this, make a picture. These numbers look familiar because we just did this yesterday. So 2.19 negative, I want this. The table only gives me the left side, so I must calculate 1 minus to get 98.57%. So the chance is very high, almost 100% chance that I'll get more than 23 successes if I try 100 times to look for what I'm looking for, if the success has a probability of 1/3 of appearing. So we should get the same answer. We did get the same answer because I didn't really change anything. All I did was rename the variable of interest by dividing it by n. Similarly, the problem for ESP. Okay, so the steps are the same. I have to check and verify, as we did before, that n times p is bigger than or equal to 10 and n times 1 minus p is. So that will work out. Then we calculate the new mean and standard deviation for the sample proportion. That's what p hat is. I standardize and I draw a picture. Drawing a picture. 5.77 is way out here. It's off the chart, but I know that means that it's so unlikely, we say, the chance of being here is, 6 standard deviations away. It's an outlier so far that the chance of that happening is 0. So again, the result that we had for ESP, the chance of somebody just guessing being found to have ESP is so unlikely it's 0. Then I have a few more problems with the same sort of thing. Find the probability that the number of Catholics in a sample of size 100 will be less than or equal to 26 with the information given. What's the information? Suppose the population is 25% Catholic. In a sample of 1,000, we expect about 250 Catholics. In other words, we expect a proportion of the population is 25% Catholic. Okay, so that's the true proportion is 0.25 if the variable is Catholic. So be clear, x equals, in this case, so you could do the XNPK, approach, but the answer is not going to be solved using the binomial. It's going to be used using the approximation because it's going to satisfy the criteria in this case. So x is equal to the number of Catholics out of Oh, I lost my sensitivity for some reason. Okay, I'm gonna reboot. Hold on. Sorry, my device seems to have trouble. I keep on getting a virus warning. I probably should heed it. Looks like my iPad isn't even launching right now. I would buy another tablet if it wouldn't take a month to arrive. Okay. I'm in. I'm back. Sorry about that. Oh wait, we're talking about Catholics. So X here is the number of Catholics. You always have to say out of. So you write out of how many? A population of 1,000. A sample, sorry, of 1,000. That's the sample, right? So find the probability that the number of Catholics in a sample of size 1,000 will be less than or equal to 260. So what I want to do, again, to motivate this problem, clearly x is binomial. With an n of 1,000 and a p of 0.25. But it's also approximately normal with a mean, this is supposed to be a 0, with a mean of NP, so N times P is equal to 0.25 times 1,000. So that's 250. Of course that's bigger than or equal to 10. And N times 1 minus P is also greater than or equal to 10. If you just want to punch it in, it's it's 1,000 times 0.75, so it's even bigger. So that's going to be greater than or equal to 10. So it satisfies the criteria that you need to verify for this to be approximated nicely by a normal distribution. So the mean would be N times P, which we figured out was 250, and N times P times 1 minus P square root, which is okay, N times P is 250 times 1 minus P, which is 0.75, and then you take the square root, which is 18.25. It's a little bit messy, but you have the answer on the page, you can follow along. So that's 18.25. So that's if I'm using the count variable, but look how the question was phrased. In the first part, it asks me to find the probability that the number of Catholics in the sample of size 1,000 will be less than or equal to 260. Oh no. You guys with the black screen. Sorry. Always something. I need a checklist to do this. So I can repeat that, that's no big deal. You can follow along if you do as I say and print the notes. You can follow along with what I'm saying. Maybe it's best the screen was black. So there you go. Those are my calculations, but they're neatly done here. So the question I want to answer is, what's the probability? Oh, I actually did the calculation of the standard deviation wrong. So anyway, it's 13.69. I actually want to answer the question that there's less than 260 Catholics. Is that right? Yes. So I want to answer the question that there's less than 260 Catholics. So that's the question here. To answer it, now that I've used the normal approximation, here is the variable I want to use in approximation. So I just standardize, and I get a value of like a z-score for the z-table, and I want to find this 0.73, so being 0.73 standard deviations from the mean. What's the probability? When you look it up in the table, you'll get 0.76, so 76%. There's 76% chance that less than 260 Catholics, it's a high chance, that you'll find less than 260 Catholics. 30% chance that you'll find more than 260 Catholics, right? 30, almost 34%. If you wanted this other side, but that's not the question. Okay, what if we answer the question for the proportion of Catholics as opposed to the percentage? So, sorry, the number. So if 260 is what I'm interested in, .260 out of 1,000 is also the same as 0.26. So if you answer the question using the proportion and its parameters, you should get the same result, and that's what I show here. Again, verifying if I was to start from scratch that we can do this. So checking my criteria, step 1. Step 2, find the new mean and standard deviation. For the proportion, sample proportion has a mean of 0.25 and a standard deviation p times 1 minus p over n square root. Make sure you can punch this in your calculator. I'll give you a minute, see if you can calculate that value. You're going to multiply 0.25 times 0.75 divided by 1,000 equals, and then use a square root to get this number. Okay, make sure you can get that. That will be the mean and standard deviation. The question was, find the probability that the sample proportion is less than or equal to 26%. Standardizing that with these parameters, I get the same result, of course. All right, so if you're using a different set of parameters for the different statistics, you will only get the same answer if you do it right. Okay? All right, then I have some other problems. You guys can practice these. I'll leave those for practice. I'm not going to do all of them. All right. Let me just see. So now I just have a bunch of exercises, a ton of exercises. So don't get lost in the fog. This is all practice for you. Now I want to spend a little time discussing how to make your estimation of the probability exact, not approximate. So this is for exact approximations. To make it exact, we need to compensate for the fact that we're losing or gaining some density artificially. Going back to the depiction of the spiked histogram. Remember this. So right now all we're doing is calculating the probabilities, saying what's the probability that in this example with x having the parameters as a binomial has the parameters of n equals 20 and p equals 0.5. Okay, with those parameters, this is the histogram that I can draw, and it looks symmetric and bell-shaped like. And if you tested it, you'd find the the normal properties exist, the 68, 95. You could verify 68, 95, 99.7% rule. it applies here. So when I calculate probabilities, I'm using the spikes, however, right? What I've done so far, I'm just using these spikes. So I'm calculating, if we smooth this out, you can imagine I need to cover those rectangles, but okay, that'll have to do. So I'm going to calculate these, you see, using the normal distribution. The problem is that you see there's kind of gaps in stuff, you know, and in particular, it's something about, look here. If I'm talking about 7 as a discrete outcome, I'm talking about being right here. But if I'm speaking about 7 as a continuous outcome, remembering that we don't talk about being at certain values, we always build density, right? We have to put, in this case, we build, the technique I'm going to show you, we're going to build rectangles around each of these observations to build density, and we're going to take advantage of that. So instead of calculating or estimating the normal distribution starting here, if I want to go less than 7, I need to consider this. This is also part of the 7th outcome. So how do I do that? This approach is known as a continuity correction. Now let me tell you, I can quiz you on this, but I'm not going to put it on the final, okay? But you might come across questions like this, and it's really important to practice. It's really important to understand that going from from discrete to continuous has a catch, and you have to be aware that there's, we use a lot of approximations, but there's ways to make them more precise. And one of those is to, in this case, is to make a continuity correction. So I have all these formulas here. Maybe it's menacing, so don't worry about this too much. Let's just look at a few problems. So the kind of problems I've been giving you, let's look at the problems I've given you now that you're familiar with them. So here's one. So just use what I wrote up there as a summary once you understand what we're doing. So here's the problem. Remember, same thing. Binomial distribution, parameters are n and p, 100 and 1/3, and I want the probability that x is greater than 23. The approximation is okay. We already checked that. N times p is greater than 10, n times 1 minus p is greater than 10, so that applies. And I can find the mean and standard deviation, so that's all good. Now, step 3, so that was 1. Criteria 2, find the new parameters. And 3, the new parameters for the variable being a normal. And now the third part is to compute this, but exact, making a correction. What do I mean? What I mean is, and I use this CCF, if I want to get the probability, if I want to compute the probability that more than 23 successes are observed, oops, apologies here, do that again. So 23 is here, say. Okay, so that's my bar. That's my attempt at a bar on this tablet. Okay, so I want greater than 23. So greater than 23, if you just think there's a histogram all around, if I just do this, greater than 23, right, so then I'm going to get all this and everything before it. But what about this piece? The continuity correction involves accounting for this piece as well. And the way you do that is, rather than going to 23, we've built a bar that's 1 unit around each spike. So it's 0.5. It's 0.5 on either side. So it's 0.5 on either margin. We say margin here, okay? So on either side. And so what we're going to do is go from 23.5 instead. Sorry, 22.5 instead. Okay, this is really messy. Let me do this again. Let me clean this up. So what we have here is 23. What we have here is 23.5 on this end. And what we have over here is 22.5, right? So that would be this end here. And 23.5 is this end here. So those are the thresholds of the bar. So what I'm going to do is answer the question going greater than 22.5 instead. So I'm going to rewrite this as the probability x is greater than or equal to 22.5. By doing so, I actually am answering the question much more precisely, using the normal approximation by making an adjustment, the correction for the shift from a discrete distribution to a continuous distribution. So if you don't have any questions, I'm going to finish this problem. So I'm answering now this question with a continuity correction, and I use the greater than or equal to denote that I want to go larger or equal to 23.5. Since here we're in a continuous distribution, I actually just need to write greater than 23.5, but anyway, that's how we do it. Okay, so then standardizing this, going back to my mean and standard deviation, I calculate this value. So this is a little slightly different, right? Slightly different. It's going to be slightly larger than you had before. Should be, shouldn't it? Because we added in that extra little bit. So let's go back. Let's see. It's 98.17 here. And what was it over here? A few more. This one here. No questions? 98.57. And if we go back, should be bigger, 98.57. Why is it smaller? Oh, because I did it wrong. Okay. I did it wrong. That's why. Now I see what I did wrong. Sorry. If I want to answer this for greater than or equal to 23, I gave you the wrong answer. I'm sorry. So that's, I always catch myself, but sometimes too late. So what I've answered here is if I want the whole bar, bear with me. The question that I answered, this is answering if you want to include 23. So this is the same as including but What if you don't want to include 23? What would you do? So just the original problem that I have written in the notes. If you wanted to include 23, higher than 23, excluding the bar completely, you would do something different. So let's draw that over here on the side. Let's say this is the bar for 23, and this is the histogram bar around it. And I want to calculate, you can imagine the next one is here beside it, and that's 24. I'm making up these numbers. Okay, that's 24. I mean, I'm making up the bars if one is higher than the other. And I want to start at after 23. So after 23 means that I include the bars after 23. So in that case, I'm going to start, where am I going to start? My correction will be to start here, 23.5, and that's the problem that I solved on the next page. So the one that I drew here, sorry for the confusion, is for 20 greater than or equal to 23, but this one is for the probability x is greater than 23, so excluding the density around 23. I would have to start at 23.5. So that's what I do next. And because I've adjusted going here, instead of here, I lose this little bit. Okay, so this is the correction. This little bit makes the estimation much more precise. That's why the number is smaller. Okay, so as I explained to you, when you solve a problem, solve them a couple of times. Just to check if you made some error. Don't look at your work. Cover your old work and repeat completely if you have time on a test or a quiz situation. Solve it twice in maybe 2 different ways to make sure you have the same answer. Okay, so you guys can spend time looking at that. The number here, the final answer is smaller. Okay, so read through that. Let's see if there's any problem I can try that I'm interested in. So this is just very repetitive. Try the exercises. Try the exercises. Cover the answers. See if you can get the right answer, okay? I prefer to not give you the solution so you work everything out on your own, but that's just not feasible right now. So use it to your advantage, not as a false sense of security that you have the answers. Actually try and replicate the answers on your own. Okay, so tomorrow I'm going to move, so because we've talked about x, the count random variable, that's the symbol I use. So the count statistic, so that's the sample count. This is the sample count, this is the sample proportion, and now we're going to go back to the sample mean. And that's where we will start tomorrow. You can watch the videos. I have the videos for this page 31 and 32, I believe, and 33 on Moodle. So watch those before tomorrow's lecture. Okay, you should be watching all this stuff. And then I'm going to actually start here tomorrow on page 35. So I'm going to let you go because I'm going to post the quiz. You can get yourself organized before I launch the quiz online. So you guys have a good night. Good luck. Thank you, and I'm sorry for the black screen. Send your questions to me, all right? I'm going to post I said I would be posting an attempt to answer quizzes that people missed or didn't do well. So let me know which quizzes you want repeats of. I haven't heard from you guys in a while. I guess you're working on other courses or just dealing with the complications that we're all dealing with right now. So just keep in touch though. Let me know where you need some help. Try and spend a couple of hours a day on stats so it doesn't pile up. We are in the home stretch now because we're finishing Unit 5 and we're going to start Unit 6, and that's what we're going to do till the end. You'll see in the final exam distribution, I have a list in Unit 6 where I provide a breakdown of the distribution of the coverage for the final exam, and you'll see that 40% of the final exam will be on Unit 6, because Unit 6 is a culmination of everything you've learned. So I put most of the weight there. So keep up for the next few weeks and you're going to be just fine. Okay, good night and good luck.